Homework 11, Polynomial Functions, Video 7, Intercepts. In a previous video, I mentioned that we would discuss the middle behavior of the graph later, but first we were hashing out the end behavior. Well, to determine the middle behavior basically boils down to locating your intercepts. Now, there are more things we can find in the middle besides intercepts, but we're going to start with those. And I've got a couple of examples on the board. Example 1 is f of x equals the quantity x plus 2 times the quantity x minus 1. And g of x is the same function except it's x minus 1 to the second power. So let's take a look at these intercepts. The y-intercept is predictable. For the y-intercept, you just find f of 0, or more generically, you substitute 0 into your function. So if we substitute 0 into this one, we get 0 plus 2 times 0 minus 1. 0 plus 2 is 2. 0 minus 1 is negative 1. And our y-intercept is negative 2. To find the x-intercepts, you solve the function equal to 0. And if you'll notice, this function is already factored, which is going to make solving easier. X plus 2 times x minus 1 is equal to 0. So we set each factor equal to 0. X plus 2 is equal to 0. X minus 1 is equal to 0. And when we solve both of those, we get x equals negative 2 and x equals 1. So we've got our y-intercept and we've got two x-intercepts. So what would this graph look like? Some of you might be thinking, I could just FOIL that out and it's a parabola and you would be correct. So we could just take advantage of that. Now, we didn't analyze end behavior, but if we were to FOIL this out, it would start with x squared, which means that both ends rise. So we could draw a pretty quick sketch of this. We know the y-intercept is at negative 2, so let's go down here to 2, down the y-axis and put a dot. We got an x-intercept at negative 2, and we've also got an x-intercept at 1. Now, based on the previous video, we could also locate the vertex, but let's just capitalize on what we know. Both ends rise, so both ends have to point up, and I have to go through all three of these points, and I know it's a parabola. So it'll look something about like that. Yeah, nothing really revolutionary there, but wait until the next one happens. G of x equals the same thing, except a square on the x minus 1. Let's start with the end behavior, which I didn't do last time, because it's a discussion on intercepts. But if you were to write out all three factors and multiply their leading terms, the leading term for the polynomial would be x to the third, which is left falls, right rises. So already I know I'm going to get a different looking graph because the left end is different than this left end. To find the intercepts, we could do the same thing. For the y-intercept, we just substitute 0 for the x, and we get 0 plus 2 in parentheses times 0 minus 1 in parentheses squared. 0 plus 2 is 2. 0 minus 1 is negative 1. Don't forget the square. Exponent happens next, so the 2 stays put, and negative 1 squared is 1. And then 2 times 1 is 2. So we get a different y-intercept. For the x-intercepts, we still have to solve the function equal to 0. So we're going to solve x plus 2 times x minus 1 squared is equal to 0. But this function has the exact same factors as the previous one. It's just that one of the factors has a square on it. So when we solve it for the x-intercepts, we're going to get the same values by setting each factor equal to 0 and solving. So we get x equals minus 2 and x equals 1 again. So these two graphs have the same x-intercepts, the different y-intercepts, and different end behaviors. So what would this graph look like? Let's see if I can fit it parallel to the same height as this one. Our y-intercept is now positive 2, but our x-intercepts are still positive 1 and negative 2. Now sometimes when you're sketching a graph, to remind yourself of the end behavior, what you can do is go to the extreme corners of the graph and draw some arrows. For example, to say the left falls, I'm going to draw an arrow pointing down on the left, down in quadrant 3, and to say the right rises, I'm going to draw an arrow pointing up in quadrant 1. Now, I'm not going to connect those arrows to draw my graph, they're just reminders of the directions the ends need to point. So I kind of run into a dilemma here. This graph has to start down here, cross all 3 intercepts, and end up pointing up. The dilemma is, and I'm going to draw this lightly because it's going to get erased, if I start low and cross through all 3, then I'm going to be pointing the wrong direction on the other end. How can we fix that? Oh, just turn around. Okay. Up, intercept, 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 turn around and go back up. Oh, but wait a minute. If I'm down here and turn around and go back up, I'm going to cross the x-axis again, but there is no x-intercept over there. I have no other place to cross the x-axis, so that didn't work either. Well, how can we sketch this graph so that I hit all 3 intercepts and the end behavior works? Well, here's how. There are 2 types of x-intercepts, ones that you cross and ones that you don't. In this first graph, we did cross at each x-intercept, but you can be an x-intercept by touching the x-axis and then turning around. So, let's take that into consideration. If I start low and cross that one, I missed it, so I'll make the dot bigger. It's kind of a sleazy way to hit the dot, but it works. Turn around, cross through the y-intercept, and I just learned that if I cross the x-axis again, I won't be able to come back up. So instead of crossing it, let's just touch it, turn around, and keep going. And that graph satisfies all the criteria: the correct end behavior, the correct y-intercepts, and the correct x-intercepts. But now this raises another question. We have 2 types of x-intercepts. Ones where the graph crosses, and one where it touches and turns. It would have been nice to know in advance that this was going to happen. And there's a way to know in advance that this is going to happen. So, what do you think in the second function could have predicted that this graph was going to touch and turn at 1? Well, retrace where the 1 came from. The 1 came from the x minus 1 factor, but didn't that factor have a power on it? This power can affect whether or not the graph touches or crosses. But it's not just the fact that it has a power, it's what type of power. In the next video, we'll analyze x-intercepts a little more deeply and discover how the exponent on the factor can impact whether you cross the x-axis or touch the x-axis and turn around.